Okay, this video is intended to be a brief overview and example of an application of what we call manometry. This is something that we've been discussing in class and is one of the most useful tools and concepts to understand in fluid mechanics because it has wide-ranging applications that you'll use as students all the way through research at high levels. So just to briefly recap, the idea of a manometer, the most general type of which is called the U-tube manometer, is a tube that interconnects two sources. We'll say this is A, this is B, and will be filled with some fluid, which we refer to as a gauge fluid. That possesses some specific weight, which we'll call gamma G for gauge. And the idea here is that if we call this PA and PB, we can use the difference in the height between the difference in fluid levels between A and B to infer the pressure difference between those 2 points. So in this case, we would say that PA minus PB is equal to gamma G times ZB minus ZA, where Z is defined as positive upward. Okay, so this is a really ingenious and an intuitive tool for measuring pressure differences because it simply has to do with pressure balanced out by the additional weight of a column of liquid. I've used manometers in countless real-world settings. I've built them and been able to get data with them that rivals, the quality of data acquired using expensive pressure transducers. So it's a very good manometry is a very good thing to understand. My personal favorite application of manometry comes from shows up in the world of one of my hobbies, that is auto mechanics. Specifically, we're going to talk about the way you would use a manometer to balance a motorcycle engine. Okay, older internal combustion engines are fed a mixture of fuel and air by virtue of what's called a carburetor, right? And I'm not going to get into the nature of operation of a carburetor, but the idea is that they consist of, essentially tubes with these little bowls full of fuel slung below them, and what controls the amount of fuel and air that enters the engine, is going to be the air flow rate through the throat of this carburetor, All air that enters the engine has to go through this tube, and as air flows faster, we'll learn later about this, but you can take my word for it now that as air flows faster and faster through this tube, the pressure is going to get lower and lower. And so when you have a multiple cylinder engine, let's consider the case where you may have come on, I want to paste. Let's consider the case really oddball engine here. Let's say we have an old Kawasaki or Triumph or something that has 3 cylinders. You don't see these very often, but they're kind of fun. It's important that you make sure that the same amount of air and the same amount of fuel is entering each of those cylinders. This is what's called synchronizing an engine. And the way that people will typically do this is because the pressure in the carburetor throat is related to the amount of air flowing through the carburetor, they will connect a tube to each of these carburetors. Carburetors often will have a little tube connection built onto them for exactly this purpose. And these tubes will be connected to a version of a U-tube manometer that actually has 3 branches instead of the 2 that we were talking about earlier. make that a little bit nicer looking. Okay. So we'll have 3 carburetors connected to 3 branches of a manometer, and our gauge fluid inside of the manometer is going to consist of what's called automatic transmission fluid, which has a specific gravity of about 0.87, leading us to a density, right, G, of around 870 kilograms per meter cubed. Let's go ahead and put that in black so you can read it more readily. Okay, so let's pretend we have some 3-cylinder motorcycle engine that's running very badly, and we, being, do-it-yourselfers, decide we're going to build our own manometers to synchronize the engine. We build this interconnected network of 3 tubes, fill it with automatic transmission fluid, and what we find is that once the engine is running, we get these uneven liquid levels on each tube, right? Well, manometry, this intuition, should tell us that, well, that means that there's a different pressure at each carburetor, which is the source of the problem. So let's go ahead and say that this first leg, right, cylinder number 1, is at a height of 15 centimeters below the bottom of the tube, or above the bottom of the tube. The second leg is going to be at a height of 7 centimeters, and this third leg will be at a height of 4 centimeters. Okay, so this is what we're given. What we're asked to find is going to be, what is the pressure difference between cylinder, well, we forgot to number these, 1, 2, 3. What is the pressure difference between 1 and 2? And what is pressure difference between 3 and 2? Okay, that is, if we were to say that number 2 is what we're going to call a reference, how far are we going to have to adjust cylinder 1 and cylinder 3 to match it? So this should be fairly straightforward, and it's simply going to be the same manometry equation that we talked about in class. So we have A, we have B. Let's go ahead and tackle part A first. Okay. Solution A. P1 minus P2 is simply going to be equal to, here it comes, gamma ATF Z2 minus Z1. Hey, that's precisely the same equation we used when we only had 2 legs on our manometer, right? Well, that's the beauty of manometry, is it doesn't matter how many legs you have interconnected. The pressure difference between 2 points is always going to be proportional to the height difference of your gauge fluid. So if we actually plug in, right, 870 kilograms per meter cubed, and our 15 centimeters and our 7 centimeters, what we're going to get is that it's negative 682 pascals. That is, there's a larger vacuum on 1 than there is on 2. Okay, that usually means that there's more air flowing into cylinder 1, and so it's going to be trying to run faster than the other cylinders. For part B, right, same thing. P3 minus P2 is going to be equal to gamma ATF times Z2 minus Z3, which, if we plug in these values, is going to be equal to 256 pascals. That is, the pressure at 3 is larger than the pressure at 2 by this quantity. Okay, so let's do a little thought experiment now. Let's add a C to our find list here. What if, our intrepid do-it-yourself mechanic is seeking not just to measure the pressure differences between each leg, but also looking to figure out what the gauge pressure is on each leg, that is relative to the atmosphere. How would he do that? Well, the atmosphere is simply another pressure source, right? We have 1, we have 2, we have 3. These are all generic pressure sources or pressure taps. If we wanted to measure the pressure at 1 and 2 and 3 relative to atmospheric, we could simply add, trying to draw this without making a mess, we could simply add another leg here, which rather than being connected to a carburetor would simply be left open to the atmosphere, right? And if we did this, we could still compute the pressure differences between individual carburetors, but using the manometry equation, we could say, for example, if this is at a height of 5 centimeters, right? We could say that that the pressure at 2 minus the pressure at the atmosphere, right, is going to be equal to gamma ATF times Z2 minus, we forgot to name this, we'll call this A, minus ZA, which would give us a pressure. I have to compute this very quickly. Equals 870 times 9.81. Right, there's our specific the specific weight of automatic transmission fluid, and this is going to be equal to that times, in parentheses, 0.05 in meters minus 0.07, which gives us negative 170 pascals, meaning that cylinder 2 is under 170 pascal vacuum relative to atmosphere. Finally, the last little sort of conceptual question we might ask is, let's say our do-it-yourself mechanic is particularly unlucky, and his engine is so out of whack that that cylinder 1 here, right, just starts to climb and hits the top of the manometer, and he actually gets slurped up by the engine, right? What design changes to the manometer might be made to mitigate this problem, to prevent the engine from actually pulling up and actually ingesting the automatic transmission fluid that you're using as your gauge fluid? So this is a question I've posed to students in the past, and two answers have sort of emerged, right? One of those is the idea of just making the legs of the manometer longer, right? This permits you to achieve a larger, for example, a larger Z1 without topping this line and dumping stuff into the engine. Or the other option is to use a fluid with a larger specific weight, because, right, the same pressure difference can be represented by a smaller height difference if this quantity gets larger. Okay? This is why often you'll see manometers, if they're sold, right, if you're buying them commercially, you'll often see them coming in with different fluids, and each fluid is going to be tailored to a different pressure range. So something like synchronizing an engine might be filled with a fluid that has about the same density of water, right? That's for smaller engines. If you were getting a manometer to synchronize something that pulls a lot of air through these carburetors and has really, really, really large pressure vacuum, or really large vacuum pressures, then you might use a manometer that's filled with mercury, okay? Something that has a much larger specific weight and therefore won't give you the same pressure or the same change in fluid level, and is therefore less likely to max out and actually cause you to to slurp up whatever liquid you're working with. So that's a quick overview of an application of manometry, and I hope you found it informative and interesting.